In the mid-20th century, there was a raging debate between Einstein and many influential quantum physicists over the nature of something called entanglement. But what is entanglement? Well, to understand that, we're first going to need to know a couple other concepts in quantum mechanics, one of which is spin. Now, quantum particles don't exactly spin in the classical sense, but they do have angular momentum, and in a certain measurement axis, that can be defined as either up or down. You can think of it as clockwise or counterclockwise. This spin can be in something called a superposition, where it's in multiple states at the same time, as proven by the famous double-slit experiment. Every possible outcome has a different probability, as described by something called the particle's wave function, and when measured, the wave function collapses into a single output. With all this knowledge, we can now understand entanglement, which is when the state of two particles are correlated, in this case always being opposite, even when they're in superposition. Quantum mechanists believed that the two particles actually influenced each other's wave functions, so that when measured they would always be opposite. Whereas Einstein believed that every particle, when entangled with another, formed a plan with it, with every measurement direction, in which they would always be opposite. The experiment that disproved these hidden variables had three measurement directions randomly chosen for each of the two entangled particles. There were two possible plans for Einstein's hidden variables, either all of them being out on one and all of them being in on the other, or one being flipped. If we take every possibility for both of these plans, we find out that both of them have a greater than 50% chance of having opposite results, with in being one and out being another result. With quantum mechanics, however, once we do the math on how the wave function could collapse, with a little bit of trigonometry to determine the chances if different options are selected for the angles, we find out that there's a 50-50 chance for them either to both be the same or to both be different in terms of being in or out, which agrees with experimental results. This is the famous Bell Inequality. Einstein required more than a 50% chance, which disagreed and thus disproved him.